Well, thank you. I don't say no to any invitation to France, so that's like a hint. So I'm going to be strictly talk about random matrix theory for random matrix theory's sake, meaning that the game is you decide upon some ensemble, some probability measure on the space of n by n matrices, and you ask what happens to the eigenvalues as n gets large. Okay, so there's all sorts of wonderful historical motivations for doing this sort of thing. I won't talk about these applications at all, right? I'll just take the point of view that we inject randomness into systems to understand typical behavior. So you're trying to understand the typical large linear, the spectrum for the typical large linear operator, and that should be enough, right, to get you out of bed in the morning. On the other hand, the most interesting thing for me about random matrix theory is that it's in trying to understand eigenvalues of random matrices. We've discovered important new points of attraction in the space of distributions, right? Important new distributions. We've discovered new distributions looking at random matrices, and these objects have shown up in all sorts of different models that seem to have nothing to do with random matrix theory. And it's not sometimes the case, it's always the case that these discoveries have been made because of some integral structure. There's some special ensemble in the class that we're looking at for which we can do exact calculations, right? So what I'll try to do for you in these next 4 talks is describe a relatively different approach, a newer approach that's much more probabilistic and much softer. And here the point of view is you understand the large dimensional limit of the matrix ensemble is a continuum limit. And you try to understand these eigenvalues rescaled in the appropriate way as the eigenvalues of some continuum, i.e. differential random operator, right? And in particular, just for today, I'm going to give a qualitative introduction to the stochastic area operator, which is a random Schrodinger type operator that captures Tracy-Widom. In fact, a whole 1-parameter family of generalizations of Tracy-Widom. Okie dokie. So the setting for that is I need a large random Hermitian matrix. And if you grab a typical person on the street and say, give me an n by n Hermitian matrix, they would probably just make it as random as possible. So they would fill up all the top triangular stuff with IID entries and then just fold it over. So as random as it can be, maintaining the symmetry. Yeah? And for anything better to do, let's say all the entries are mean 0 and mean square 1. Right? So just standardized symmetric or Hermitian matrix. Okie doke. So now, that's not the right scaling to take if you want to look at n goes to infinity. If you don't want the spectrum wandering off, filling the whole line, you got to take that m and hit it by a 1 on square root of n factor as n gets large. And the best way to see that is to do a little calculation that goes back to Wigner. So if I take and understand what happens to the typical eigenvalue, right? So if I take, is this the, there it is. So if I take lambda 1 to lambda n are the eigenvalues of this rescaled matrix, right? So all the variances are now 1 on n, if you like. And I look at the empirical density of states, which what I'm doing here is I'm putting a delta measure at each random eigenvalue coordinate, summing them up and dividing by 1 on n. This is the empirical counting measure of eigenvalues. Or it's really the distribution of if you grab an eigenvalue at random, one of the n eigenvalues uniformly. That's same thing, okay? Then the calculation of Wigner, he did it in a slightly different setting, and it had a weaker result. But as n goes to infinity, this random object converges weakly, almost surely, to this quote-unquote semicircle law, right? So this is just an argument that this is the right scaling. So this is the Wigner semicircle law back in the 50s. And this is a law of large numbers, and it's a global statistic. And what we really want to study are local statistics, right? What happened to individual eigenvalues. So, one, of course, interesting case is, say you look deep into the bulk, right? So you have this profile of eigenvalues, right? Between -2 and 2. This is a semicircle. Here's 0. So this is the kind of question, maybe you have big n eigenvalues, you look at the guy in the middle, which should be near 0. This is the kind of question Wigner would have been more interested in. And it's pretty clear that if you look at the n on 2th eigenvalue, there's order n eigenvalues to the left and order n eigenvalues to the right. So this character only has kind of order 1 on n space in which to fluctuate. So you would like to take maybe the middle eigenvalue, subtract 0, which is to do nothing, blow that up by n, and understand what happens to that. All right? I won't talk about those kind of questions at all. Even though those are, in a sense, more natural questions, I'll be talking about what happens at the edge. Okay? For all 4 lectures, I'll be dealing with edge statistics. So what happens to the maximal eigenvalue? Oops, okay. Now, and this gets us to Tracy-Widom. So, you got to realize that something like just knowing the Wigner semicircle law doesn't tell you that the biggest little o of n eigenvalues don't wander off to infinity. But if you're willing to assume maybe a higher moment, like fourth moment of your entries, it's in fact a theorem that lambda max converges to 2 and lambda min converges to -2. The spectrum really sticks to the edge, right? And so for a local fluctuation at the edge, the question there would be to ask, if I take lambda max and center it, right, by its limiting position, blow it up by n to some factor gamma. It's not now no longer a priori clear what that gamma should be. Will this converge to something, right? Is there a random variable this converges to? Oh. Right now, I just say fourth moments on the entries. Right, because that'll just give me that the biggest eigenvalue does converge to 2, right? But it'd be purposely vague. Okay, but so the first answer to that question was in a very specific assumption on entries. And this is due to Craig Tracy and Harold Woodham back in the mid-90s. And they showed that if you assume the entries are complex Gaussians, standard Gaussians, that if you subtract 2, you blow up by the gammas n to the 2/3, you ask for the distribution of this rescaled biggest eigenvalue, it converges to this rather exotic looking object, right? So you can read it off, the exponential, the running integral, a little polynomial factor, u squared SDS. And u is the solution to Panlevet 2. That's Panlevet 2. It's this ODE. It's a nonlinear ODE. You got to specify something. And it turns out if you just specify its behavior at infinity, you have a unique solution. All that's, it's still surprising, right? That this is a distribution function. This is what comes out. All right, now of course, we know this object to be, so this is in the mid-90s. Knowing that this is universal for random matrix theory, that was a long story starting in 2000 for matrices with all finite moments. This is, work of Soshnikov, and that was slowly chipped away by Soshnikov and Pesch. But the full universality has only been proven in the last few years. These competing camps of Tao and Vu and Erdos and Yao, et cetera, et cetera. So this is universal within random matrix theory. You don't need the complex Gaussian assumptions anymore. What's more exciting, of course, is that this is universal outside of random matrix theory. So this is the object that appears in the one-point fluctuation of the whole KPZ universality class. So things like the flux of Taysup, the longest passage time and last passage percolation. And again, these are things that I won't talk about directly, right? But this is an important object. All right, so I'm getting the impression, I didn't know ahead of time, but just sitting in the first few lectures, it's pretty clear. I think a lot of you know the story, but for completeness, I just thought I'd run through where does this, where does this come from? What are the bunch of miracles that allow you to compute this, or allow Tracy and Woodham to compute this? So this is, of course, because this, in the case of complex Gaussians, this is the Gaussian unitary ensemble, and it's an exactly solvable model regards to spectrum. Okay, so you push down, you have this measure on the space of matrices, complex Gaussian entries. And then you can try to integrate out the eigenvector coordinates and understand what's the density on eigenvalues, right? And this is explicit formula. You got a Gaussian weight on each eigenvalue coordinate times this product of differences squared, right? So this keeps the eigenvalues from flying off to infinity, and this keeps the eigenvalues from ganging up on each other, right? There's these two qualitatively competing factors. This is the van der Maan determinant, of course, squared. A product of scalar functions is itself a determinant. So you can write this whole object as a determinant. And then because you can change, you can do row operations within the determinant, you can write it as all sorts of different determinants. But there's a right way to do things, right? And the right thing to do is to write this joint density, this is up to some proportionality constant, as some different constant perhaps, times the determinant of where the ij entry of this matrix is a fixed kernel evaluated at lambda I, lambda j, and that kernel is the that kn is the kernel given by the projection under the span of the first n Hermite polynomials, right? So that object is explicit in terms of classical orthogonal polynomials. So in principle, this already tells you if you want to ask any detailed question about the spectrum of GUE, you're asking an analytic question. The improbability is gone, right? You just need to know something, maybe very precise, but something about orthogonal polynomials. And in fact, a family of orthogonal polynomials, which you can look up in a book, all right? Sorry. Now, I mean, that formula is lovely, of course, but you're trying to say something about, let's say, the biggest eigenvalue, right? You're not going to say something about all n eigenvalues as n goes to infinity. So it's nice to have this formula, but you need to be able to integrate out. You need to be able to compute marginals if you're really going to do anything with it, right? And that's why this is the right way to write the determinant, because that projection nature of the kernel allows you to compute marginals, or quote-unquote finite dimensional correlations. So if you take this as your full density, again up to some constant, and so you want to integrate out, all but the first k coordinates, then you get a new constant times the same sort of object. And this is what we really mean by a determinantal process. All finite dimensional marginals or correlations are given by the determinant of the same sort of object. Right? So you have all the finite dimensional distributions in your hands. Right? Okay. But then, there's more. Right? So for all determinantal processes, there's a quote-unquote gap formula. Okay? And this is just general nonsense. If you have a determinantal process with a nice enough kernel, I'm going to leave it to Alexander. You'll explain all of this, right, in great detail, of course, so I can be vague, right? So if you have a nice determinantal process on n points on the line, right, so again, some object like this, you need some, I wrote down some, if the kernel is non-negative, symmetric, perhaps trace class, blah, blah, blah. If you want to compute the probability that you don't see any points in some set B, this is given by another determinant, and what it is a Fredholm determinant. So this is the determinant. You take your kernel, you view it as an operator on L2 that defines one, and you look at the Fredholm determinant of identity minus that kernel acting on L2 of the set B in question. All right? Fine. In our case, the projection onto the first n Hermite polynomials, that's a finite ring kernel. All right? So this has a little expansion, and I ran out of room, but that truncates after n steps. Right? So this object is, right, if you like, now if I want the distribution for the biggest eigenvalue, B is the set from t to infinity. Right? So if I want to ask what's the distribution of the biggest eigenvalue, that says that there's no points above some level t. Right? So for all n, you have an explicit formula for the distribution function of the biggest point. Right? And that's wonderful, and all then you see that really what you need to do is pin down what happens to this kernel, right, as n goes to infinity. And so, kind of a first form of the Tracy-Widom distribution is the following, that this distribution function, which is L2, the Fredholm determinant acting on L2 of some half line of this kernel made up of Hermite functions, converges to this Fredholm determinant of the quote-unquote array kernel. And this is just what happens to that projection kernel in the limit. All right? And then, in fact, okay, so I wrote this is what you have to do, right? Is you take that projection kernel on Hermite functions, you rescale in the appropriate way, in the way given by the theorem, that you see this. And so then, in fact, you can define a whole point process at the edge, right? You take all the biggest points, right? The biggest eigenvalue, the next biggest eigenvalue, down to the 27th biggest eigenvalue. You want to take their limiting correlation. It'll be given by the appropriate, K 27 by 27 determinant in this array kernel. So there's an array point process on the line that tells you what to do. All right, and then the Pain-Levé formulas. I mean, that's the real work. This is not so exciting. The real, incredible work of Tracy-Widom, of course, was to show a closed Pain-Levé formula for this Fredholm determinant, right? But that comes after. Okay, so just again for completeness, outside the complex Gaussian case, if you say, well, that was weird, how about real Gaussians, right? Well, you can do it. And you can actually do quaternion Gaussians too, if you like. So there's a self-dual quaternion ensemble of Gaussian matrices. And all that happens then is these are, again, solvable models. You replace the product of differences squared by just the product of differences in the real case, or the product of differences to the fourth power in the symplectic case. And you talk about the beta 1, 2, 4 ensembles, or the Gaussian orthogonal unitary symplectic ensembles. When betas 1 or 4, because they're determinantal processes, they're so-called Pfaffian processes. So you replace the scalar kernel, right, this projection kernel, with a 2x2 skew symmetric kernel. But again, it's still built out of Hermite functions. You can push the analysis through. Tracy-Widom did that in subsequent papers. So there's an F1 and F4. There's a, you might have missed the notation, but I called that Tracy-Widom 2 for a reason, right, even though it came first, right, because it corresponds to beta equals 2, the complex case. And then in the 1 and 4 case, there are again explicit formulas in terms of Painlevé. So F2 is the complex case, and there they are for the record, right? So you have these three classical Tracy-Widom distributions that are at least 1 and 2 come up in the whole KPZ universality class. So to finally get at what I'll be talking about is you go back and you say, well, we have these kind of like God-given matrices that turned out to be solvable, right? These real complex and quaternion cases. And let's just go back and consider the structure of their eigenvalue densities. So I'm just going to write down this quote-unquote beta ensemble. So I have products of Gaussian weights, right? Then I have this van der Maan product of differences, show general beta power, right? So again, for 1, 2, and 4, those realize the eigenvalue densities of GOE, GUE, and GSE, okay? But they're perfectly lovely densities on endpoints on the line, right? This defines a point process. And if you write it in this kind of Gibbsian way, you can tell yourself a story that what you're doing is you're saying, okay, this looks like the coulombic interaction, right, with a quadratic potential. So this is some sort of of course, that's the coulombic interaction, that's the right interaction, electrostatic interaction in 2 dimensions, right? It's wrong in 1 dimension. But you say, okay, we have a caricature of a Coulomb gas on the line that happens to be exactly solvable for 3 special values of temperature or charge or whatever you want to call that parameter. That seems neat, right? And and that's really a point of view taken very seriously. So Peter Forrester has a several 100-page book called Law of Gases and Random Matrix Theory. That's basically about this. Okay, and in this case, we call this I'll discuss as we go on several different beta ensembles. This is the beta Hermite ensemble, again, because of those special cases, they're tied to the Hermite polynomials in an intimate way. All right, so again, here I'm just writing here that you think of this as a 1-dimensional Coulomb gas, and the kind of question you might ask, well, you might ask all sorts of questions, but you can ask, is there a general beta Tracy-Widom law, right? So in this ensemble on endpoints on the line, there is a biggest point, there's an extremal, there should be an extremal distribution theory, and whatever it is, that should be Tracy-Widom beta, all right? Now, of course, when you move off beta 1, 2, and 4, there are no good formulas for the correlation functions. All right? There's a lot of work in this area, but there's no formulas for the correlations that people can effectively take asymptotics of. All right? So all that exact structure goes out the window. All right? But there is, of course, I asked the question because the answer was positive, right? There is a general beta Tracy-Widom law, and this is a theorem of Jose Ramirez and Valentin Varag and myself from back in 2009. And here's what you do, all right? So you bring in a random differential operator, which is now referred to as the stochastic area operator. So you take a Brownian motion, standard Brownian motion, and you take the operator is the following: negative second derivative, so negative Laplacian plus x. If you stop there, that's the area operator. That's just the differential operator that gives you the area equation. And then you add to this a random perturbation. The random perturbation is 2 over square root of beta. So this is the only place beta appears, times the derivative Brownian motion. That's a white noise. Of course, Brownian motion is nowhere differentiable, so that's a random distribution. All right?
So we are not supposed to ask yet what this means rigorously.
No.
So far it doesn't very much, right?
Right, yeah. So implicit in the theorem is this makes sense, right? But that's part, yeah. All right, so you write this thing down, all right? And you take this thing, you view it as living on the half line, on L2 of the half line. You fix Dirichlet boundary conditions at the origin. Part of the theorem is this thing is actually, its associated quadratic form is bounded below this discrete spectrum, okay? Let's call its eigenvalues, lambda 0, lambda 1, these capital lambdas. And the theorem is, if you take little lambda 1, little lambda 2, these are the ordered eigenvalues of that beta ensemble from the previous slide, just that density on points on the line, right? And then you scale them the same way you scale Tracy-Widom, right? Thing centers at 2, you blow them up by n to the 2/3. You take any finite number of ones of those points you want, right, from the beta ensemble, yes? And then, jointly in law, those converge to the corresponding extremal points of this random area operator. All right, that's the theorem. Okay, so I do right here, right? Bx being a random distribution is not at all clear at this point that this makes any sense at all, right?
Excuse me, as you said, convergence in law means convergence in terms of finite dimension
finite dimensional distributions.
Plus 27.
Yeah, whatever. You take any number you like, and you get convergence in finite dimensional distributions of the point processes. Absolutely. Okay. So yeah, so indeed some work is to make sense of H beta. Today I'm gonna do that tomorrow. Today I'm just gonna tell you stories about what you can get out of this world. All right, so now, so what I'm doing here is I'm giving you a formula that's just defines Tracy-Widom and defines Tracy-Widom beta sans random matrix theory, right? So what this would mean is that, so right here, the largest limiting point of this beta Hermite ensemble converges to the negative ground. So this is annoying, right? Because in random matrix theory, you're trained to talk about the biggest eigenvalue. In random Schrodinger, you always talk about small energy levels. So you always go back and forth with a minus sign, and I now do it easily, but I know it's going to be annoying. So it converges to the negative ground state for the stochastic area operator. So what you can do is you can say, well, if I want the negative ground state, I should write down the corresponding variational principle and minimize over the correct space. So almost equivalent to the theorem is the following, that the negative Tracy-Widom distribution is this is the quadratic form associated with a stochastic area operator, right? I just hit F, H beta acting on F, I multiply by F on the other side, and I integrate, right?
But Tracy-Widom depends on T.
What's T?
It is a function.
That's a distribution. Yeah, that's the distribution. This is not the distribution, right? I mean, there's good things and bad things about this point of view. This just characterizes the random variable, saying, I'm writing down a functional Brownian motion, and this object, its distribution, is your favorite formula.
How do you know that the minimum variance is unique?
I'm going to prove that tomorrow. You don't, right? Yeah. All this stuff, right? But I'm saying, if you believe that this random operator had discrete spectrum, right? And if you form its energy and minimize, that should give you Tracy-Widom, right? Tracy.
Is it even obvious that the right-hand side is positive?
No, absolutely not. Right. And so yeah. So that's not. I mean, so I'm just kicking the problem around on one hand, right? But assuming it is, and assuming. So here's what you do. So you boldly just write down this quadratic form because it's the natural one, and you minimize over what's the right space. Well, I said you should have Dirichlet conditions, so you want that. You want to normalize in L2, and then you want the good part of the energy to make sense, right?
So this is TWB, not FB.
Say that again?
It is not FB.
No, it's not FB. It's the actual random variable, right? And it's just some ridiculous nonlinear function of a Brownian path.
But you also can write analog of FB.
Yeah, I can. Yeah. I can only say so many words at a time. Okay. But no, I will. So yeah, so this is a characterization of Tracy-Widom, the actual distribution, all right? And so as several people have raised, even this is right now on an incredibly shaky ground. So because while this object is clearly positive, there's a B prime here, right? So what does the stochastic integral mean, right? And there's no a priori bound below on this thing over this space, right? So that's one thing you need, and just as a teaser, right? I would say the following. Say, look, this form is densely defined, so certainly this form is wonderful on functions f that are compact, support, and smooth, so leave me alone, that's how I define it. But still you have to minimize, right? When you minimize, you're going to have to show things are bounded below. And, well, you got this bad term that's f squared dB. You don't like differentials of Brownian motion, so you should integrate by parts, right? That's what you don't like a derivative, you integrate it. you try to get rid of it. And so here's something that you would try first. You say, well, I'll just refer decent enough functions. This is certainly true, right? And what do you need to do? You need to hide this bad part of the energy, this bad part of the form, under the good part, right? You need to control the stochastic integral by the positive part of the energy, right? So you say, okay, that's wonderful. I got an f prime, I got an f. Let me just Cauchy this thing. I can put a small little constant here, right? And hide the f prime squared under this appearance, right? But then you get the constant times b squared f squared, right? And if you know something about Brownian motion, you know that Brownian motion of x, as x gets large, right? Do the iterated logarithm, it grows like square root of x times log x, right? So when you square it, that goes like x log x. And so you miss by a mile, right? You cannot fit Brownian motion squared under x. So it looks pretty shaky, right? So it's not just a perturbation argument that this thing makes sense. So you have to be more clever. I just wanted to mention that because it's not so easy, in fact, to show this thing is defined below. All right, but I think more interesting than these proofs, which again I promise tomorrow, is just where does this thing come from, right? Where do you find this random differential operator? Okay, so this comes from the fact that we had GOE, GUE, GSE, and blah, blah, blah. And I said, let's just generalize at the level of densities. We get these beta ensembles. There's no correlation functions. And we can talk about these random points, not eigenvalues. But in fact, they are eigenvalues. There's a family of matrix models, in fact, simple matrix models, that realize all these beta Hermitian ensembles. And this is a theorem from around 2000 or 99 by Eilman and Iona Dimitriou. And it's the following. So I'm going to build, it's here. I'm not building anything. I'm pointing to a random tridiagonal, random Jacobi matrix. All right, so this H and beta is a symmetric random matrix. Along the diagonal G1, G2, down to Gn, these are just IID normals, mean 0, variance 2. Okay? And on the off diagonals, you have a bunch of what I call chi random variables. So a descending sequence of chi's, chi n minus 1, chi n minus 1 beta, chi n minus 2 beta, right? And the theorem is, for all beta, you compute the joint eigenvalue density of this Hn beta, and it's given by that beta Hermitian ensemble, right? And these chi's, what this means, I mean, the notation is a little bit weird, but if beta is an integer, right? So this index is an integer, we're calling them chi's because in that case, it really is the square root of a classical chi-square distribution, right? More generally, it's what's called a gamma random variable. These chi's, the chi r, has this density, just some constant times, some simple random variable. Importantly, they're positive. So these are positive random variables on the off diagonals. These are really random Jacobi matrices. Okay? So you have a class of simple matrix models. Now this is the point of view. The point of view is that, okay, that still doesn't allow you to compute anything at the level of correlations or statistics, but in probability, there's what gets dressed up as the objective method, right? You should always scale the biggest thing you possibly can, right? So if you can't scale the eigenvalues, you should just scale the whole object, and the whole object is the operator, right? So in some sense, what we're going to show, well, in a real sense, we're going to prove eventually that the appropriate scaling limit of these random tridiagonal matrices is stochastic array, all right? And then a kind of thing like this should be true had been conjectured earlier. Oops, I'm getting ahead of myself. I want to tell you, okay, I was getting excited. I should tell you, let's talk about where these tridiagonals come from. why they, I apologize. Why, how Edelman and Dimitriou saw this. And it's really kind of one of these funny stories. So, any numerical analyst, I'm going to tell you where these tridiagonals come from. So any numerical analyst on the planet knows that you can tridiagonalize a symmetric matrix and keep the eigenvalues the same. All right? So you take any symmetric matrix, and there's a sequence of rotations by unitary matrices on the left and right that'll reduce things to a tridiagonal matrix and keep the spectrum the same. All right? Here's the algorithm. It's called the Haussweiler algorithm. So let's take, M now is not anything random per se, but it's just a symmetric matrix or Hermitian matrix, and write it in the following way. So, here's just the first coordinate. Here's the lower n minus 1 by n minus 1 block matrix. And this bold-faced M is the first, the rest of the first row and the rest of the first column, which are, of course, the same because of symmetry. All right? And now what we're going to do is we're going to hit it. We're going to conjugate it by a unitary matrix. And the unitary matrix is going to have the form 1, 0, 0, U. And the U is an n minus 1 by n minus 1 matrix. And when you do that, and this is how you pick U. You pick U, so I'm writing U, these are the columns of U. What you do is you pick the first column of U to take this object, your first row, and rotate it over to just its norm. All right? And then you fill the rest of the columns of U just to be orthogonal, right? You just make them, you just fill them up with orthogonal stuff. And if you do this, right, obviously you leave the first entry alone, right? you rotate this first column. You need to put the norm there, everything else 0. That's already looking like tridiagonal stuff. Same thing happens here. And then you get a new symmetric matrix down below, n minus 1 by n minus 1. And now you do it again, and then you do it again. And you slowly reduce this thing to tridiagonal form. All right? So, a little exercise to convince yourself that if this m was really GOE or GUE, you can do this algorithm, right? You can just carry it out, and you can track what happens to the distributions. This is because the Gaussian is unitary invariant, all right? And what you'll see is exactly what we had on the previous slide. When you rotate, right, what you're going to have here is a vector of n minus 1 Gaussians, all right? And the norm of n minus 1 Gaussians is a chi-squared. The square norm is a chi-squared, all right? And when you get down to this stage, this will be this n minus 1 was an n minus 1 by n minus 1 dimensional GOE or GUE, and statistically this doesn't change, right? You don't care what the rotations were, right? You don't change the statistics at all, so you can do it again. And you can push this through. And for beta 1 and beta 2, you get exactly what we said. And then you need a genius like Alan Edelman to say, well, there's only one place to put the general beta, so let's stick it there and reverse engineer the Jacobian, because that's really what's happening, right? So to think about that, the point of view to take here, take the point of view that what they're doing, the Dimitri-Edelman theorem, it's placing a measure down on tridiagonal matrices, right? You're building it up entry-wise, but think about it matrix-wise. So what I write here is define tridiagonal matrices with random entries, capital A's and capital B's. So I'm using capital A's and capital B's for random variables here, right? And I want to draw this tridiagonal matrix from a density, yeah? And the density I'm choosing, so I'm using little a's and little b's for the formulas in the density, yeah? So this is the density on the vector AB, or if you like, the tridiagonal matrix, right? So this is exactly, right? On the diagonals, the a's, product of AI squares, those are independent Gaussians, right? And if you pair these products of BI squares with this little factor BI, those are your chi's, right? And you can see that this looks a little GUE because, of course, upstairs you're getting a trace of the matrix squared. But it's a tridiagonal matrix, it's a different ensemble, right? So they're saying if you draw the tridiagonal matrix according to this law, then these are the eigenvalues.
So is it possible to explain this then for those who haven't got it yet?
Oh, okay, well, of course it's possible. I hadn't had it, so, I mean, what you need is you need a map, right? You're mapping from tridiagonal coordinates to eigenvector coordinates. But there's, the full eigenvalue eigenvector coordinates, those are too many coordinates, right? So what you're really mapping from are eigenvalues and what are called norming constants, right? And those are the first coordinates of each of the n eigenfunctions or eigenvectors. And so that's actually the spectral map that goes back to Sphego, or maybe even Jacobi. So this mapping between tridiagonal coordinates and eigenvalue norming constant coordinates, it was like sitting on the shelf, right? So you put these two things together, and those are the beta ensembles. So you have to do a Jacobian calculation, but that's where it comes from. So I don't have it prepared, and I would make a mess of it if I try to do it on the board. But I put these two things together, and so once I talked to Bohigas, I gave this talk a bunch of years ago, and he told me that and I have no reason not to believe him. He told me back in the 70s, he and Maida had the beta ensembles. They had the tridiagonal matrix models, but he's like, we couldn't see what good they were, so we didn't even publish it. Right? And that's because they had a very different point of view. The point of view was like, this isn't going to help you compute correlations, right? You have to deal with the operator itself. Okay, so now I'm back to taking the limit of the operator itself. This was just supposed to be some hint of where this possibly comes from. All right. So now you say, this is the conjecture of Edelman-Sutton that led to the stochastic area operator. So what you want to do, again, Hn beta, those are that's our tridiagonal matrix model filled with Gaussians and chi's. And the idea is you're going to scale that whole thing like you would scale lambda max in GUE, right? So you took lambda max, you subtracted by 2, and then you blew it up by n to the 2/3, right? And there's this sign switch, so you're going to take actually 2 minus lambda max because I want a positive operator in the end. But if you want to scale it at the level of operators, what you should take twice the identity minus your tridiagonal matrix, blow the whole thing up by n to the 2/3, and this squiggly line is to indicate conjecture. You know, they suggested this should look like, in the limit, the stochastic area operator as operators, or at least at the level of spectrum. So, you know, what's the heuristic for where this would come from? So remember, okay, what's this Hn beta, right? You have these Gaussians, fixed Gaussians, meaning mean 0, variance 2, just fixed, you know, they're not moving on the diagonal. The only thing moving around are those chi's, right? You have chi's of degree beta times n minus 1, beta times n minus 2, all down those off diagonals, all right? So if you want a little exercise, you know, you can make precise the statement that, and remember they're normalized by beta, square root of beta on n, that these random variables that appear on the off diagonals of that tridiagonal matrix model, but they look like for large n and moderate k, they look like 1 minus k over 2n plus a Gaussian. This is a mean.
The central limit theorem.
It's the central limit theorem. Yeah. Yeah. So just, yes. So, you know, but you just take the point of view that's an equality, right? And this is the heuristic. You know, you just treat the central limit theorem as an equality and you stick it in the entries, right? And forgetting about the fact that this doesn't look so good for big K when K is of size n, you just forget about it. You just stick this in, you know, you just replace all the chi's normalized by what the central limit theorem predicts. And then you think about what happens at leading order. Well, at leading order, you have 2's on the diagonal. And the leading deterministic part on the off diagonals are going to be a bunch of minus 1's. So if you think about everything but leading order, what this rescaled matrix model looks like is n to the 2/3 times the tridiagonal matrix with minus 1's on the off diagonals and 2 on the diagonal. That's the second difference operator, right? The second difference operator at spatial scaling n to the minus 1/3, right? And then, you know, another completely satisfying little exercise is you go to the next order, right? The next deterministic order, which is given by these k on n's, k on 2n's, right? But of course, multiplied then by n to the 2/3. And you convince yourself that if that thing has a limit as a continuum operator, the only choice is for it to be multiplication by x, right? And then you have, at the end, after invoking the central limit theorem, you have a matrix filled with a bunch of Gaussians with an n factor, right? And you compute a variance and you convince yourself, well, at the level of the continuum limit, the variance is blowing up. So you got a Gaussian process whose variance is blowing up, you say that's white noise. And that's what they wrote, right? But it's true, right? It's true, okay? So that's where this conjecture came from, and we'll go through improving on that or making that all rigorous tomorrow. But what I want to do now is I want to totally switch gears, and I want to answer, you know, what I want to do is I want to answer your question, Alexander, okay? Is I want to give you a formula for the distribution function. And to do that,
I knew that.
yeah, you know, you got this random Schrodinger type operator, and you want to count eigenvalues, right? And you can use a very classical tool, and this is Sturm oscillation or Riccati substitution, which I'll remind people of in the nicest possible setting, right? So let's pull back and imagine you have a wonderful Schrodinger type operator. So some tau equals minus second derivative plus q for a nice deterministic q, smooth, like 0. You know, if you want to take q0 right now, that's fine with me. And let's put it on a finite interval, on 0L, and you have Dirichlet conditions on both points, all right? And you want to find an eigenvalue of this thing, okay? A Dirichlet eigenvalue for this problem. All right, so one method is, you know, the quote-unquote method of shooting, or it's related to Sturm's oscillation theorem, and here's what you do. You fix a lambda, right? Okay, you fix lambda ahead of time, and you think about an initial value problem. It's a second order equation, right? And you want it to be Dirichlet at 0, so you decide, for a fixed lambda, I'm gonna find a function psi such that psi 0 lambda equals 0 at 0, and, you know, just fix its derivative to be 1, right? After the fact, you can normalize, right? It's a linear equation. And then what you do is you just let that thing rip, right? And, you know, for whatever lambda, you can solve this thing. And when you get to x equals L, you look if you're at 0. If you're not at 0, you don't have an eigenfunction. So then you just have to tune lambda to crank the solution down to 0 at 0, right? This gives you a mechanism. It's the shooting method for counting eigenvalues. And so what this means, you know, is that, you know, the number of eigenvalues, so you fix a lambda, any level lambda, the number of eigenvalues under level lambda equals the zeros of its initial value solution between time 0 and L, right? That's classical stuff, all right? And then if you like, you can rework that in terms of a first order problem. This is what the Riccati substitution allows you to do. So you simply bring in the log derivative of psi, right? And you write down the equation for that. So if you bring in this is all it is. This is the Riccati substitution. So you define P to be the log derivative of psi, and then that solves a first order equation, but with a quadratic nonlinearity, all right? And now, where does P start? Well, psi prime over psi is infinity at 0, but that's okay because this nonlinearity will bring the solution down immediately, right? And every time psi touches 0, right, psi crosses 0, right, from top to bottom. So whenever psi crosses 0, P hits negative infinity. And by following the coordinate 1 over P, you can see that it immediately reappears at infinity. So the Riccati solution starts at infinity, hits minus infinity, kicks itself back to infinity, and goes again. So the number of eigenvalues that lie less than lambda, you can write as the number of explosions of this P function to minus infinity before time L. Okay? And that's all totally classical stuff. And then you just want to import this for this terrible potential, right? For Q equals X plus white noise on the whole line, not just 0 L. All right? I'm not really going to prove this for you either. I'm just going to tell you what it is today. All right? Now, let's flash back. Here's the equation. You got P prime equals Q, blah, blah, blah. But now Q is B prime. So how do you interpret, the only way to interpret an equation like that is to interpret it in the differential sense, right? And so this is an Ito equation. So I build this little SDE, the solution of this SDE, so dP in time is, 2 on square root of beta dB, that's d Brownian motion, and this drift, which depends on the spectral parameter, lambda, all right? Now this diffusion, you can start at infinity, and if it hits minus infinity, you pick it back up and you do it again. And the theorem is, a corollary from having the stochastic area operator representation, is the distribution function for the general beta to Tracy-Widom distribution is the probability that you take this diffusion, you begin it at infinity at time 0, and you ask for the probability that it never explodes. Wait, say that again, I'm sorry. An explosion means this random process can get to minus infinity in finite time. Due to this minus P squared. I mean, here's a little fact. See, I mean, let me draw a picture, in fact. Okay? So another lovely thing about this diffusion is you see the spectral parameter appears as lambda, appears linearly with the time parameter. So what you can do, actually, and I write this here as a note, you can shift the spectral parameter to a starting time. All right? So you can instead think of the diffusion dpt just equals 2 on square root of beta dB, that's Brownian motion, plus t minus pt squared dt. And what you do is you ask for this thing to start at lambda, and ask for that to never explode. Non-explosion means getting to minus infinity in finite time. All right? So let me draw a qualitative picture. Let's imagine lambda's negative, because I drew it negative. Now what happens, what does this drift look like? This drift is negative everywhere until you get to time 0, right? And when you get to time 0, there's this special parabola, t equals p squared. Everywhere in this parabola, the drift points up. Everywhere outside this parabola, the drift points down. Okay? So for this diffusion not to explode, right, starting from it has to wander down, and eventually it has to hit this magical parabola. If you start off at a big positive lambda, so you're asking for the distribution function under lambda where lambda is big positive, it means you're starting this diffusion deep into the parabola where the drift is positive, right? That improves your chance of not exploding, because to explode to infinity, you would have to tunnel through this parabola and get to the place where the drift points down. And so the kind of thing you can prove by classical theory is that if this diffusion was homogeneous, if you cross out time, this thing explodes with probability 1, right? In finite time, All right? Injecting this time gives you the chance of non-exploding. And what's amazing is that when you don't have the time dependence, you can write down even the distribution function for when it will explode. You can write down all sorts of exact formulas. And now we only introduce this linear inhomogeneity in time, right? And for beta equals 2, we have these Pain-Levé formulas for this probability. But it's still a big open problem to prove Pain-Levé formulas in general, even though we have this very simple kind of description of this object. Okay, does that answer your question? Okay.
Excuse me, I got a little confused with notation. Where do you get this T term from in the original equation?
This guy?
The T guy.
Yeah, I did this because the potential is x plus white noise, right? And on one hand, with the operator, x is natural, but people go nuts when you drive a Brownian motion by space, right? So they like time. So I switched to t's for times, but it just comes from that. It comes from that. Okay, and likewise, the distribution function of the kth largest point for the general beta ensemble is the probability that this process explodes at most k times. Right, so after picking it up and starting again, picking it up and starting again, if it only explodes k times, the probability of that event is the distribution function for the kth biggest point. Right? So you can describe all the general beta Tracy-Widom distributions and its subsequent points through this little Ito process. Okay, so here's the deal. If you don't know or like this stuff, these kind of SDEs, here's a nice little exercise. What you can do, put the dB on the other side, right? So you have dP minus dB, or dP minus B, right? And then you write P as P plus B minus B, and you square it out, right? And what you can see is that this diffusion P minus the scaled Brownian motion actually solves at ODE. An honest to God ODE with diffusion, with coefficients that are Brownian motion and Brownian motion squared, right? So there's nothing crazy going on. So it's a random ODE with continuous coefficients. And then that's a very easy format in which to see that you really can start this off at positive infinity, and you can explode at random times to minus infinity, depending on what the Brownian path does. So it's a much more concrete place to work this out. Okay, so I'm going to take 2 more minutes. Okay? Okay, because what I'll do is I want to show you that this whole stochastic area thing isn't just a pretty face. We can actually do quantitative things with it. All right. So here's something we can do very quickly with this setup. So on one hand, we have this variational principle, which we don't know that makes sense, right? But we have it. And on the other hand, we have this Riccati diffusion description of the distribution function for Tracy-Widom beta. Okay, so here's a corollary of the main theorem. This is again in the original paper with Jose and Berlin. For any beta, we have the following asymptotics, tail asymptotics for any Tracy-Widom beta, right? So the right tail looks like e to the minus 2/3 beta, a to the 3/2 with corrections. And the right tail looks like e to the minus beta on 24 times a cubed in corrections. Of course, for beta 1, 2, 4, you have Pain-Levé formulas, and you can get much more precise information. But what I'll show you is you can do this in a couple lines using probability, at least a leading order. And if you work harder, you can get further detail. So large Dumas and Berlin-Farag have gotten out to the polynomial order for the right tail, using the same kind of idea as I'll express now. So I'm just going to do the left tail. I'm going to give you the upper and lower bounds. So there's four bounds in each of it. There's 2 tails and 2 bounds in each tail. So here's a proof of the left tail upper bound. All right. So Tracy-Widom beta is apparently the ground state eigenvalue for the stochastic area. So that means if I want to compute the probability that Tracy-Widom beta is less than some big negative level, I need the ground state to be bigger than some big positive level. All right. So the ground state is a minimization problem. Right? So if I just forget about the infimum, I get an upper bound. Right? So what I'm doing here is I'm just sticking in any test function f into the variational principle. Right? You agree that this is an upper bound for any f I like. Right? Okay. Now, the only thing random here, I'm going to choose a deterministic f. So this is just becomes a question about a Gaussian variable, right? Because even if you don't know anything about probability, you can prove this. For any deterministic f, the integral of s squared dB is equal in law to a normal random variable times the square root of the 4th moment of the function. And you can see this because Brownian motion is Gaussian, so dB, a little increment of Brownian motion is Gaussian. Brownian motion is independent increments, so this is really a sum of independent Gaussian, so it will be Gaussian. Then you can compute variances. All right. So then you just pick the right f, and this is the right f to choose. So if you play around with it, the intuition is if you want a big ground state, the way you get a big ground state is for the potential to be flat someplace. If the potential is flat on a nice big fat set, the eigenfunction can just go live there and accumulate a lot of mass. All right. So if you optimize the right thing, what you do is you find this function, this little square root of a minus x. Very simple. And this other nonsense, this is just to fix it to be in the right space. Right? Square root of a minus x is in 0 at 0. And its derivative is an integral at a. So if you just fix it up to live in the right space, and you stick this thing in there, you do some very simple calculations, you see all these a cubes. And it's wonderful. Right? Remember what we're supposed to get is e to the minus a cubed times beta 24. So that's it. That's the proof. Right? This is the minimum. Minimum, right? Yeah, so it's the minimum of those three functions, right?
And the superscript plus?
The positive part. Oh, that should be below, right, usually?
Yeah, usually below.
All right, well, here it's above. Okay, so yeah, it means the positive part, right? The positive part.
But how far what was the correction so you can go? How far you can go?
We can get the right second order. We can get the right second order by being very, but I know I should stop. I'm going to stop. I got a proof of the lower bound, but tomorrow's getting up, and I know you're not supposed to be late for lunch, so we can get the lower bound too.
Lower bound, yes.
Yeah, it's fantastic.
Okay, so let's thank very much, Brian. So we have 5 minutes questions. Mm-hmm.
My question is very short.
Okay.
Why don't you do same analysis in the bulk?
Well, because it's been done. So, so in the bulk, you get a random Dirac operator, and that's work of Valco and Varag.
So it's same.
Yeah.
Is this, well, it's actually, I mean, the bulk is a lot more subtle, and they've really only carried out the operator limit for the beta unitary case, not for beta Hermite, for technical reasons.
But if somebody maybe not you, but your colleagues, so you have for bulk.
Yeah, that's what I just said. I said, so Valco and Varag have an operator for the bulk.
Yes. And you even have, they have some more terms in the asymptotics, if I'm correct.
Yeah, so okay. All right, so that's older. So in the bulk, what came first in the bulk was the analog of the Riccati diffusion. The operator actually came later, and at the edges, we find the operators first, and we get the Riccati by corollary. The Valco Varag, like 2010, gave a diffusion whose certain hits gave you the statistics in the bulk, and they used that in the same way, here to get asymptotics for a big gap.
But I believe there was even interesting story that original Dyson's hypothesis was not quite correct for the second term, and you, I believe, correct.
That was Valco Varag, because that was a bulk thing. Yeah. But yeah, we have higher order, and I'll talk about the hard edge this week. And for the hard edge, we can get actually all the way out to the constant, right? Not the right constant, but for the hard edge gap, it's easier. Yeah.
So any other questions? So probably okay. Lunch is waiting for us then. Thank you very much.